Thank you to Nihar and the organizers for this opportunity. It's really a great pleasure to visit India. I've been several times before, but never to the south of India. There was this famous meeting organized by Bikash Sinha, which some of us knew. He's no longer around, so-called Indian Quark Matter that he organized in Jaipur. And I was at a couple of those with my wife, took a fantastic trip across Rajasthan and so on. And so I've been to India a number of times scientifically, but never to the south. And my family and I, my wife and my adult daughter are with me, and we took this opportunity to take an absolutely extraordinary trip, starting in Chennai, looping down through Pondicherry, through Thanjavur, Chettinad, Madurai, Munnar, winding up in Cochin for the last couple of weeks. And it's been absolutely extraordinary. So thank you for the opportunity. I also very much look forward to our scientific discussions this week. And before I start, one of the most exciting parts of our trip was our visit to Thanjavur, and in particular this fantastic museum, the Royal Palace Museum, which has a beautiful collection of Chola bronzes. And I'm sure everyone in the room knows what Chola bronzes are. They're justifiably internationally famous, and they also have a physics connection. And for those of you who haven't been at CERN, so here I am in the museum. The lighting was a bit bad. The photo isn't great, but you see, they had a whole collection of these tremendous sculptures from a long time ago and some more recently. And here, you can't read it here, but I've blown it up. Nataraja statue of Shiva dancing is displayed at CERN, representing the cosmic dance of particles. And if you have been to CERN, you know very well this statue. It's really centrally located at CERN. On the right here is the CERN hostel, which when you go to CERN, you will stay at. And on the left here, do you see a little corner? This is the main physics building, the headquarters of the Atlas and CMS collaborations. And behind the photographer is the CERN cafeteria. So really central to the CERN campus. And on the pediment here is written, "O omnipresent, the embodiment of all virtues, the creator of this cosmic universe, the king of dancers, who dances the Ananda Tadara in the twilight, I salute thee." So very beautiful sculpture, bringing together deep Indian history and philosophy with the kind of science we do to understand the basic rules of the universe at the most microscopic scale and the most macroscopic scale. So I thought that was a very beautiful connection. So let me go on to my lectures, and let's spend a moment on the title. I spent some time thinking about this title. It's got three components: measuring, multi-body, QCD. QCD, quantum chromodynamics. You've heard plenty of lectures on that. We don't need, well, I will actually define it. I'm going to, sorry. So Nihar asked me to give some pedagogical lectures. I understand you've had some more expert lectures. So I'm going to actually cover material probably you've already heard, but with a little bit of a different angle. And that's not bad. It's always good to come back to things and look at them again in a different perspective. So quantum chromodynamics is our broad topic here, all the lectures. That's really what the 2 weeks is about. Multi-body means not focusing on the most elementary, simplest interactions, but really discussing what happens when we have many QCD quanta together, what new phenomena emerge. That's the nature of the Quark-Gluon Plasma and other kinds of physics we're studying. That's multi-body, and this word measuring. I am an experimentalist, as Nihar indicated. And my emphasis, perhaps different than some other lectures you've heard, my emphasis is on measurements, on data. What can we understand from the data? There are many clever theorists in our field, and they have lots of great ideas, some of which are correct, and the way to tell which ones are correct and which ones are not is actually to ask carefully what nature tells us. And it's difficult. Understanding, kind of doing experiment to understand the nature of QCD is quite challenging, and I'll spend some time on technique to give you a sense of how we do these things. I'm not going to spend a lot of time in technique. I have some stronger emphasis in a certain few points, but my goal is really to give kind of the bigger picture and not get kind of stuck in the details. So before I go on, let me just take a little survey of the room. How many in this room are theorists? Show of hands here. Okay, how many are experimentalists? Show of hands. Okay, we're overwhelmed by theorists. That's good. So I hope you will learn how experimentalists think about and try to test what you guys are thinking about and proposing. And theory and experiment have to come together. And a good theory idea is a great theory idea if data also confirms it. So not every idea is of equal value, and we'll see what happens as we go. So here is the schedule. I've broken them down into lectures, but the materials are really quite uneven. The first lecture today is pedagogical, really kind of starting at the beginning. I'm not going to get a lot into multi-body or many-body physics. And this lecture just kind of give us a basis, kind of a foundation to move ahead from the experimental point of view. The bulk of the material is actually in lecture 2. So these are not going to be divided evenly in the 4 days. I hopefully will finish this a little early and be able to go on to lecture 2 already today. Let's see how it goes. So the first 2 are really on the physics, and then the third is something new, which I suspect you haven't heard about. And this is how to bring theory and experiment together in a truly rigorous way using a tool called Bayesian inference. And this pervades, science, pervades cosmology and many other branches of physics, and is relatively new in our field. But it is really the way in a rigorous, highly controlled fashion to bring together complex theory and modeling and complex, very heterogeneous data, and ask deep questions about how well do we really have full consistency over a broad array of data for complex calculations. So that's a very important and rapidly developing area, and I want to spend time on that. And if I get to lecture 4, this is some new ideas I've had with colleagues on the nature of low-X physics and saturation. Let's see how it goes. By all means, please interrupt, ask lots of questions. That's what I'm hoping for. So the first lecture is on perturbative QCD and jets, and I have every expectation that most of this is not new to anyone, but let's go through it and I'll give you my angle on it. So I said I'm an experimentalist, so why not start with the QCD Lagrangian? Well, I'm not going to spend a lot of time on that, but let's just pull out the essential feature that's very important for everything we do. So this should be familiar. We write down the degrees of freedom, the elementary fields, the quarks and the gluons, and the interactions. So it's a gauge theory, same basic structure as quantum electrodynamics, which is a lot easier, but it has one deeply important difference, and that is that the gluons, which are the photons of QCD, carry color charge and self-interact. So you get all of these complex gluon interactions, and it makes it the multi-body QCD highly nonlinear and complex. So the gluons interact among themselves, generating complex structures, and that makes an absolutely enormous difference. So now let's talk about the nature of interactions in general. We have 2 quanta here, 2 basic particles. It happens to be electrons, could be quarks, could be gluons. They interact. And we want to characterize their interaction by a momentum transfer. How hard is the interaction? How much momentum is being transferred in the interaction? And just by simple uncertainty principle arguments, if the interaction is soft, small momentum transfer, we're probing the interaction at large distances. As we go harder and harder, larger and larger momentum transfer, we're probing smaller and smaller distances. Just an uncertainty principle relation. So momentum transfer and physical distance are completely related. Now, we also know that the vacuum is not static and empty. It's very dynamic. Virtual pairs are popping in and out of existence all the time. And that's very interesting from this point of view, because that means that these virtual pairs can screen an interaction. Well, now putting these 2 thoughts together, that means that the interaction between 2 elementary particles, the strength of the interaction can actually depend upon the momentum transfer, so-called running of the interaction or running of the coupling. That's the essential physics between the running of any any interaction coupling. So what does that mean in practical terms? Well, the way to think about this is a so-called renormalization group beta function, and there are people in the room who are very much more expert at this than I, but let's just write this down. It's a little formula here that expresses the change in interaction of the coupling G. G is related to more familiar alpha in this way, sort of natural units. It's the change in coupling with a momentum transfer scale. So let's see what the beta function looks like. For QED, quantum electrodynamics, the beta function looks like this. It's positive. What does that mean? Whoops. What does that mean? As we go down in momentum transfer, we're probing larger distances. And as Q goes down, G goes down. And so larger distances is weaker coupling. And that's analogous to the screening of charge in a dielectric material. Okay, so that's just standard electrodynamics. We're kind of familiar with that. That kind of drives a lot of condensed matter physics. Now, QCD, the beta function for QCD looks like this, and it's got the number of flavors here in the numerator. And nature tells us that we have 6 flavors in nature, and that means that the beta function of QCD is negative. In other words, as we go to smaller momentum transfer and larger distances, the coupling gets stronger. Very weird. And that makes all the difference. That is a fundamental difference between QED and QCD. As one probes at larger and larger distance scales, the coupling gets stronger. That is the way QCD is structured. And if you figure that out, okay. So here is the famous running of the QCD coupling constant alpha pulled from the Particle Data Group book. The Particle Data Group is a wonderful organization. It's actually based in my home institution at Lawrence Berkeley National Laboratory. I suggest you just Google PDG or Particle Data Group, and it's got a wonderful compendium. It is the place of reference for all new particles discovered. Kind of it curates and declares the reference values and catalogs all particles. It's got wonderful reviews of high energy physics theory and experiment. And in particular, this plot is sort of the standard plot of alpha S. It updates it every few years. This is from 2022. And you see all kinds of measurements here across decades, really, probing the strong coupling constant as a function of momentum transfer Q. And you also see calculations of higher order QCD. And it's a wonderful agreement. And what you see is a very rapid change, really striking change of large coupling constant, low momentum transfer, small coupling constant, and high momentum transfer. This is really the way QCD works. And so at low momentum, the interaction is strong, and we get the profound phenomenon of confinement. This is what binds quarks together in the proton and neutron, makes this conversation possible. We wouldn't have chemistry and biology and human interactions without the nature of confinement. As we go to high momentum, QCD becomes simple. We get these kind of Rutherford-like scatterings of quarks and gluons producing jets, which is really my topic. Yes, question?
I was involved in extracting few of the points here.
Okay, good.
My question to you as a theorist, is it worth...
Can you speak into the mic?
My question to you, a theorist, that is it worth measuring more and more points on the higher Q sites? Like now that we know it's sort of the asymptotic freedom phenomena is coming up well. So any collider program, or probably the future collider programs, will keep measuring alpha S. Mm-hmm. But I will just try to know your or everyone else in this room, their opinion. Is it worth just measuring some jet observable at higher Q scales and keep extracting alpha S? Is there any further theoretical motivations to do that?
I'm an experimentalist. My personal opinion is you should never stop measuring fundamental constants. You should always, these are measurements. And while it's impressive, I think it's been a while since I looked at this in detail. Let's look at these red guys up here, and maybe you were part of this. So these red guys are all jet probes. is there another non-jet way of extracting alpha S at very high Q, and is it consistent? As experimentalist, that seems to me an interesting question. Maybe a theorist has a theory, and that would be fine, but I'm an experimentalist, and regardless what my clever theory friend should say, we need to do that. So absolutely. I think the big hole is here. I mean, this is the low Q. This is, I think, where the real, where things really are, there's big error bars, and this, you would like a lot more data here, right? It's not terribly well constrained by the data. And the electron-ion collider, some of us have been thinking about event shapes and thrust measurements and so on at the electron-ion collider. If I were to put in time, and I actually wrote for an EIC report, actually, together with colleagues, I wrote a little kind of proposal for how to measure alpha S at the EIC, and that was actually focused on, you talked about the high end, sure, should do the high end. If you had a channel other than jets, I think that'd be super interesting. But the urgent thing on this plot is down here, I think, is really to try to constrain the growth of alpha S at low Q. If we don't look, we don't know what nature has. These data, they look pretty precise. They're not infinitely precise. Is there some small effect that indicates some new physics that I can't dream of up here? You should never stop measuring fundamental constants. Yeah.
What you said, Peter, but even in the high energy domain, you see you have N3LO, which means that you are pushing QCD calculation, perturbative QCD calculation, right, to the extreme. So I don't know what the status is right now, but there are issues of resumming higher order contributions, which deserve to be analyzed.
Well, I'm guessing, as I said, it's been tough. So let me just riff here. This gray line has a width to it. I'm guessing that that's the theory uncertainty. We'd have to go back and check. And down here, check down here, the experimental uncertainty is still much larger than the theory uncertainty. If I'm right and this gray line expresses the theory uncertainty. Absolutely. So I revised my comment. Not only do you want channels other than jets, do the jet measurements better. Okay, so does that answer your question? Never stop measuring fundamental constants. Even alpha, yeah, okay, I think I made my point. Right. So, okay, good. So, right. So now a little bit on theory. Right. So we discussed a little. So in this region of strong coupling, perturbative tools don't work. One has to use the tools of lattice. And again, there are also great experts in the room on lattice QCD. Up here, where the coupling is small, one can use the tools of perturbative quantum chromodynamics. And if you figure out the QCD beta function, you get a trip to Stockholm. And these fellows absolutely deserve that. My focus, as I've already indicated, is on the high end here. Other people are talking about at this school, they're talking about the low end. My focus here is on the high momentum end. Okay, so let's start with multi-body QCD, but probably no one's talked about this at this school yet, but I think it's a very important place to start. Then let's talk about the structure of the proton. One proton, not two protons. Just start simple. Because there's some very important lessons here. And we're going to not use proton-proton or nucleus-nucleus collisions. We're going to use electron-positron collisions. Now, there's a forthcoming electron-ion collider in the US that'll start maybe 10 years from now, or a little less, but there was a beautiful set of experiments done at the Hera laboratory in Germany, at the DAISY laboratory in Germany, with a collider called Hera that turned off in 2008, just before the start of the LHC, which measured deep inelastic scattering of electrons and protons. So you have an electron coming in and a proton coming in. The electron emits a photon or a Z. It hits a quark it's a quark is electrically charge. It hits a quark in the proton. The quark carries momentum fraction x. The momentum transfer is q. And since these experiments are very simple and you can measure the scattered electron, you have complete kinematics. You know the momentum transfer and the momentum fraction in each collision with precision from the experimental data. And here's an example of an event from Hera. So virtual photon scatters off a quark, carrying momentum fraction x with momentum transfer, or so-called virtuality Q. So that's the experiment. So I want to focus on one particular thing that people measure. This is one of the most common things to do with DIS. And this is to measure a proton structure function called F2. Now, what is that? And theoretically, it is the sum over quark flavors of a term which depends on the charge of the quark flavor and the momentum-weighted parton density. Now, this is a theoretical decomposition. Experimentally, you measure the total neutral current cross-section. F2 is dominant. You're using kinematic selections. There are other terms, but you can extract F2 experimentally from the total neutral current cross-section of electron-proton scattering. So this is experimentally measured. Why is this interesting? Let's imagine this very simple model of the proton. It's made up of 3 quarks, each carrying 1/3 of the proton's momentum. Well, then F2 is going to have a delta function of x equals 1/3. It'll be a delta function. Maybe because we've got quarks in a box, maybe there's a little bit of smearing due to quantum mechanics, but basically a delta function at 1/3. So that's a simple model of a proton, 3 quarks, each carrying 1/3 of the proton's momentum. That's what F2 should look like. Very good. We can measure it and we can test whether that is in fact correct. But there's more. More generally, if partons are point-like and incoherent, in other words, they don't really interact, there's no kind of multi-body or multi-particle interaction of quarks within the proton, then the momentum transfer shouldn't matter. We hit one point-like object, it's got no transverse scale, and so momentum transfer shouldn't matter at all. So there's this limit that F2 has no dependence on momentum transfer, which is experimental observable these interactions. That limit is called Bjorkane scaling. So let's see what F2 looks like experimentally. Here's what it looks like experimentally. This is this quantity F2. This is the summary paper from the 2 big experiments at Hera, H1 and Zeus. This is the final result of the Q squared and X dependence of F2. It says F2 tilde, that's a little detail, don't worry about that. So this is a function of X, momentum fraction X, for various values of Q squared. So does this look like a delta function at X equals 1/3? Absolutely not even close. So that's a completely wrong picture of the proton. Q squared does matter, it matters profoundly. You can see a very strong dependence upon Q squared. The protonic densities are not point-like. Hadronic structure depends upon the scale at which you probe it. The Bjorkane scaling limit is not achieved here. Furthermore, now look at these green lines. These are perturbative QCD calculation using so-called DGLAP evolution. These are initials of the various fellows who developed it. And this tells, using tools of perturbative QCD, this tells how this quantity F2 should evolve as a function of momentum transfer. And you see absolutely spectacular agreement between the DGLAP calculations and the F2 measurements. You can squint and you won't find any difference between the data. I mean, clearly, these error bars mean something, so the central values aren't on the green curves, but this is surely consistent as well. Absolutely wonderful agreement between DGLAP evolution and these final F2 data, a tour de force of perturbative QCD. I would go so far as to say that this is one of the proofs, if not the proof, that QCD is the correct gauge theory of the strong interaction. It's really a magnificent achievement. So this establishes QCD, and we understand something about the nature of the structure of the proton. So more generally about parton distribution functions, before I leave this, here's kind of a summary of what we know. So if we probe the proton with small momentum transfer, remember small momentum transfer corresponds to large distance scales. In other words, we're looking with a kind of a lousy telescope that we don't really resolve much. For small momentum transfers, the proton is simple. We see valence quarks and maybe a little bit of dressing. And here is the particle data group in 2024, their latest parton distribution functions in the proton, dominated by valence quarks here at around 1/3, plus some contributions from C quarks. And remember, the momentum carried in the proton is dependent upon this axis. So if you do a momentum weighted sum of what's in the proton, this is dominant. So that's at low momentum transfer, large transverse distance scale. If we go to high momentum transfer, the proton. We're really looking with fine, with fine detail into the proton. It looks very much more complex. We see very much more structure. The valence quarks are much less dominant. The gluons shoot up tremendously. So this is kind of the summary of the world's knowledge of the structure of the proton at the moment. And when we talk about low X, and if I ever get to it, we're going to come back to this and really think about what that means to go to very low X and have these gluon densities diverge. So that's what I wanted to say about deep inelastic scattering. Let me now move on to hadronic collisions. Let me pause here, see if there are any questions about the deep inelastic scattering of proton structure before I go on. Questions? No. Okay. So now let's get a little more complicated. This is an old picture. I like it. It's from actually Tevatron days, long before the LHC, but somehow it just stuck around in my slides. So there's an antiproton here. That's the Tevatron at Fermilab, no longer operating. But it's a nice picture, so I continue to use it. Let's think about the collision of two protons, or proton and antiproton. We'll get to nuclei later. So this is much more complicated than deep inelastic scattering. We've got a beam of gluons here, a beam of quarks and gluons here. They're coming together. A lot of complicated stuff happens, and that's really our business. So, but QCD is, if you ask it the right question, it can give you some reasonable answers. And if we confine ourselves to looking at hard interactions where the momentum transfer squared is much greater than lambda QCD squared, which is the natural scale of QCD, then alpha S is small. This is the right-hand side of the evolution plot of alpha S. So we're going to constrain ourselves to hard scatterings. There's a lot of interesting physics if the scattering is not hard, but that's not my topic today. So we're going to constrain ourselves to hard scatterings. And if we do that, we can use something called EQCD factorization. Factorization means that the cross-section, we have an inclusive cross-section, proton, antiproton, goes to jet plus X or pion plus X. We measure a jet and we don't care what else happens, so-called inclusive interactions, I'll use that word often. The inclusive cross-sections to produce something is the product of probabilities, not interfering amplitudes. That's a factorization assumption, so there are blobs here. And these are not accidental. This is what QCD allows us to do, is to take probability distributions of the partons distributed in the proton. We've already discussed that in DIS. So because we've got two protons here, there are two such factors of the parton distributions coming together. This is multiplying probability. There's no quantum mechanical interference here. Interference is far subleading in the factorization scheme, times a hard cross-section, which we can use perturbative tools for. And then depending what kind of object we want to measure in the final state, a jet or a pion, if we want to measure pion distributions, then we need something called a fragmentation function, which is analogous to a parton distribution function, likewise evolves with scale. So if we want a jet, then we'll come back to jets in a moment. If we want a jet, we don't need this thing. If we want a pion, we need an additional term here. So that's the idea of factorization, and it basically makes it possible to think about high energy collisions. If everything were just interfering and just an enormous quantum mechanical problem, we couldn't make any progress. My brain is not large enough to do a quantum calculation and get some intuition. This actually is an exceedingly helpful, essential tool to think about high energy collisions, and we use factorization all the time. Even talking about a jet, when we say the word jet, in other words, this object, that has underlying it a factorization assumption. We use it because the alternative is chaos. But one has to bear in mind that it is, in a sense, an assumption, and you always have to check. Yeah. Question, yeah.
So, we all know that this factorization so far is working.
Right, but it needs to be tested.
Yeah, but do we, is there any development at what limit or where we, what limit and where we cannot, or there is some limit to use this factorization?
Where it breaks down?
Yeah.
Sure, that one always has to test it. And the way to test it is to compare perturbative calculations based on a factorization picture to measurement. And so there's a beautiful measurement from early on in the RIC program that the Phoenix experiment made of colliding just proton-proton and measuring the production cross-section of pi zeros. The simplest thing you can do, proton-proton goes to pi zero, don't care what else happens. And they measured down to very low momentum pi zeros. And they compared to perturbative QCD calculations, really quite sophisticated ones done by Werner Vogelsang, who was really an expert in this kind of stuff. And he applied at the time, the best perturbative calculations. And they found excellent agreement between pi zero production and these higher order QCD calculations down to 3 GeV. So this is by, if you just stop somebody at the hallway in CERN and say, how low can you use perturbative QCD in terms of fine PT, 10 GeV, 15 GeV. 3 GeV is the number at which the data and the calculation agree really with beautiful precision. So that's my best answer to how to test perturbative QCD. You just have to compare to, you want to do it for photons, you want to do it for whatever maybe heavy flavor. The answer can be different depending upon what your observable is, but that's a very striking result. It was kind of stuck in my mind that this picture actually applies over a very broad kinematic range, including going down to lower momentum scales than I think the ordinary, high energy nuclear physicist would give it credit for. So I think it's, again, the experiment will tell you, but that's my answer of how to test it, how to know. Okay. More questions? Yeah.
So is it really that the factorization doesn't work in the low energy scale, or is it the error related to the measurement of the last two terms, d sigma dt and?
Sorry, I didn't quite understand. Maybe move the mic away a little bit.
Yeah, so I think that the factorization works in all the scales. I think so.
Not necessarily.
Why?
Are you asking why?
So I'm saying that the last two terms, the error lies in the measurement of the last two terms. Yes. I think so. So it is related to d sigma dt and the fragmentation function by which we measure how the pion or other hadrons are formed. So is it so?
I'm not quite getting the question. Maybe.
So I am saying that the factorization is an intuitive expression.
It's intuitive, but it also can be derived. You have to calculate where the interferences are subleading.
Yeah.
It's not just a guess. I think you can derive it.
Okay, but why it shouldn't work in the low energy scale? Because
eventually, I mean, it's this, where does quantum interference, eventually, if we think about extremely soft gluons or think about, we'll get the Quark-Gluon Plasma eventually. I mean, pion production at 500 MeV from the Quark-Gluon Plasma, this is not a factorizable process. There are limits to this picture. This is relatively simple with protons. If you have multiple interactions and maybe my next slide may help understand why this might break down at very low momenta. This depends upon a cross-section, identifiable objects coming in, identifiable objects coming out. If in fact you have multiple objects contributing to a complex process, this doesn't work.
So the error lies in the d sigma dt and dH by C.
Say again?
So the error lies in the d sigma dt and dH by C. So that's what you are saying.
I'm saying you have to test it.
I mean, there is some approximation in the calculation of those terms.
Maybe, Jean-Paul, maybe. Mike, I think we need to.
You have to think of the constraint on the momentum scale here in terms of time scale. And what the factorization is telling you is that the hard processes, takes a very short time compared to the other two processes. So once this occurs, you can really think of a factorized cross-section because there is nothing else during this short time scale than the original partons. If you wait for too long, meaning going to smaller Q squared, then you have this interference effect that Peter was talking about.
Yeah, but then the question is, how long is too long?
Well, nobody knows.
Nature knows. Nature knows, and we have to ask the question. That's why I think this Phoenix measurement of the pi zero is so very interesting. Had I asked you the number before, you probably wouldn't have guessed 3. It's a surprisingly low number, isn't it?
Okay, thanks.
Okay, so maybe my next slide is related to this question. This is beautifully simple. Let me see what else I had to say here. Yeah, okay. Now let's look at reality. So this is, I think, related to your question. That was a beautifully simple picture. How can it break down? So this is one of my favorite animations. Again, a very old picture, but it works I like it. So what happens when we produce a jet? So we have two protons, and they're now protons coming in. Okay, and something happens. We pull out some quanta, and they exchange a gluon. And this guy is high Q squared. This is the high Q squared interaction. And it's highly virtual, and it evolves by shaking off some gluons here. And eventually, these gluons, we don't see free gluons in nature. Eventually, magic happens. It's very, very complex. I would say one of the most important problems in science. How do color charged objects turn into color neutral objects? I mean, this is the very deep question. Magic happens. This gluon shower turns into pions and kaons and the like, and are measured in a detector. But there's other stuff going on. These are protons. I'm not even talking about nuclei yet. These are protons. So what happens here is so-called initial state radiation. So we have a hard interaction, but we can't tell QCD what to do. It can do other stuff on the way, so you can, because there's some virtuality involved here, it can radiate beforehand, and we can't constrain this initial state radiation to be outside of the cone of interest for the shower of the parton we're trying to measure. So we want to measure this process, and it gets complicated by the shower. Well, that's one thing. But this initial state radiation really complicates things and can find its way into this cone that defines the product of the jet. Now, replace the protons with nuclei, it's really complicated. So that's the nature of the problem we're trying to deal with. But there's more going on. So the protons haven't disappeared. We've pulled out a quark and a gluon or whatever from this green and these blue dots, but the rest of the stuff is still there. It heads down the beam pipe, may also interact. You can get multiple hard interactions in one proton-proton collisions. Everything will happen. It's just a matter of how frequently. And so this should give you a sense of how complex measuring jets really is in practice. We have to deal with this underlying event, so to speak, this initial state radiation. And when we get to nuclei, that's a very, very hard problem. Okay? So this picture clear? Gives you a sense of, this is beautifully simple. Nature is a little trickier, right? So I'll play this again because I like it. So, and this should keep it in your mind, because this is really what we're trying to deal with in the experiments. So we have initial state radiation, we have a hard interaction, and all of this stuff contributes to what we actually measure in the detector. And the detector cannot distinguish what's produced here from what's produced there, and that's the challenge. We have to find analysis tools that can disentangle these different kind of contributions, because the factorized piece only applies here, right? The factorized piece, the factorization formula has nothing to say about this. I guess that's my best answer to your question. Okay. All right. So jets, super complicated, why bother? Because they are everywhere, and they are fundamental to QCD, and we need to understand them. They're produced copiously at colliders. I'll be talking about data not from S-Phoenix, data isn't ready yet, but I'll be talking about measurements from all of these detectors, which presumably you've heard of. And Gavin Salam, a few years ago, this nice compendium, well over 50% of all LHC experimental papers involve jets in some way. They are everywhere, and we need to understand them. So, okay, so here is an event display from the Atlas detector showing back-to-back jets. You can imagine, a quark and a gluon come in. It's 2 to 2, the simple Rutherford scattering. You see, this is now the Atlas barrel kind of sliced open and laid flat, and you see two back-to-back jets. They're azimuthally back-to-back, different places longitudinally, who knows where. And you see your eye can pick out very clearly these back-to-back guys. So these very energetic jets, your eye can pick them out. That's good. But the trick is you don't just want to say, oh, there's an event with a jet. You want to measure it with precision. You want to measure its energy with precision, and you also want to measure its structure with precision, and that's really what we'll be talking about. So it's a tricky game. This is very beautiful, but it's only the start of a very long road. So how do we do this in terms of analysis? The term of art is called jet reconstruction. The idea is to take this fundamental hard process. It turns, QCD does the hadronization, turns into stable particles, and then we have our detector. We have so-called calorimeters. I'm not going to talk about experimental technique at all. I'm assuming, who does not know what a calorimeter is? Don't be shy. And everyone knows what a calorimeter is? Good. Big blocks, at the Atlas detector, all of this stuff, massive calorimetry, very massive detectors. It's what it says. It measures energy. It stops particles, measures energy. There are two different kinds of calorimeter that measure photons and electrons, so-called electromagnetic, and then hadronic, which stops everything else except muons. Then they have muon detect. These are the muon detectors outside because muons go through everything. So calorimeters measure total energy, but then in ALICE we have, and all the other experiments we have charged particle tracking. So you want to put together the calorimeter measurements and the charged particle tracking in your cleverest way to reconstruct what's in the jet. Now, even thinking about that, it gets complicated because what's this massive Atlas experiment? What's all this stuff? It's a magnet. What happens to charged particles in magnetic fields? They bend. What happens to neutral particles in the magnetic field? Nothing. They don't bend. So you've got neutrals and charged particles that are initially aligned, magnetic field, they get spread apart. And there are many meters, whoops, easy. There are many meters from here to here. I don't remember how many meters the Atlas, diameter of the Atlas experiment, it's big. And so there's lots, and you can actually see the track curvatures here. And so, but, so the track winds up here in a hadronic calorimeter, but the jet is going this way. So you got to correct for that. The calorimeter, there's a lot of tricky business just to associate, calorimeters and tracks and put everything together in a way that you can analyze with precision. We're after precision. So there's a lot of art in putting this stuff together experimentally. And we want to bring things together. And even from this simple picture, let's ask the question, let's take a vote. Is there a unique algorithm to reconstruct a jet which represents the quark that produced all the spray of? Who thinks there's a unique algorithm? Obviously, answering the question, the answer is no. The answer is no. There is no unique algorithm. It's a statement of we define jets in this way, and I'll come back to what that means in a moment. So, okay, right here. So the goal, sorry, I'd forgotten how I put these in these slides. So the goal is precise comparison, or the first goal is precise comparison of experimental measurements and rigorous perturbative QCD calculations. That's what we're after. I've already indicated how complicated experimentally it is to do this. So we have to come up with an algorithm that obeys some important properties. And there's been actually decades of work and several generations of algorithm to come up with things that really work. And I'll show you in a moment how well they work. So we have to have the same jets at the so-called parton and particle. These are theoretical concepts. So partons, what comes out of perturbative QCD calculation. The particle level is what comes out of a model like Herwig or Pythia. Maybe some of you use that, which kind of models pions and kaons that we see in the detector, but based upon perturbative QCD and what we measure the detector. So we want an algorithm that gives us the same jet quantity at all these different levels, and we want an algorithm that gives us an answer that's not dependent upon arbitrary choices. You can imagine these algorithms are kind of clustering. You have to start here and then add particles as you go. And you don't want to get a different answer depending upon which particle you chose to start. So it's got to be robust against arbitrary choices. And there are two key properties that any good algorithm has to satisfy. So let's imagine we've got a jet here. Let's imagine we have two 5 GeV pions versus one 10 GeV pion that are collinear going the same direction versus one 10 GeV pion. We want an algorithm that gives us the same answer in those two cases, because QCD, the gluon shower can produce two 5 GeV pions just by some splitting, but that's not a different jet. So we want the algorithm to be collinear safe. In other words, if these two guys are half the momentum of this guy, we get the same jet. So it has to be collinear safe, cannot depend upon some arbitrary cutoff in momentum. So no no momentum cutoff on the constituents. And likewise, if we've got this configuration, we've got two hard pions, and you've got something soft in between, depending upon how we do the clustering, the order in which we bring things together, we might get one jet, we might get two jets out of this. Bad. We want, if we have soft radiation, we don't want that to disturb the answer that comes. In other words, infrared safety. So collinear safety and infrared safety are essential properties of any good jet algorithm, because if we don't have these properties, we've got a lot of arbitrariness built in that perturbative QCD just can't model, and we spoil the precision of the connection between experiment and theory. So these are tricky, and I'm not going to spend any time on this. You can have a whole lecture on the nature of, on jet algorithms. There have been really, I would say, decades of work. And this is just a list of names. I'm not even going to define them. You can well imagine, generically how one kind of gangs together particles. You start with some seed, and you bring things together, and then eventually have to have a cutoff. You say this is within the jet, this is outside the jet. I'm not going to spend any time talking about them, except that these are various algorithms, all of which work equivalently at the experiment and the theory level. They differ in how you do the recombination, different ordering of recombination, and different sensitivities to event background. Some of them produce jets that are circular, some of them produce jets that are lumpy. A jet is a definition. It is not an absolute physical object. The goal is to have a definition that works the same for theory and experiment. And there's a beautiful work by Galvin Salam and Gregor Soyez and Matteo Cacciari in the and the LHC was developing something called FastJet, and here is the website, and they basically all of jet physics is here. I mean, they really did a fantastic job of bringing everything together. They developed this new algorithm called anti-KT, which is used universally at the LHC, and I advise you to go there to learn about jet physics and how to do this both theoretically and experimentally. It was an absolute tour de force, and has really had a tremendous benefit on the LHC program to bring all of these algorithms together in some kind of unified picture. So that's, as I said, I'm not going to spend time on that. I do want to look at the results. So let's look at the end results here. Sorry, this figure got a little screwed up here, but here is a measurement from the CMS collaboration of inclusive jet production of proton-proton collisions and tests of perturbative QCD. So this is the inclusive cross-section of proton-proton goes to jet. And you can see many of orders of magnitude. Not sure why the quality is so poor. It should look better on the slides if you download them. Many orders of magnitude, 10 to the 15 down to 10 minus 3 in picobars per GeV, and vast range from 100 GeV to 2 TeV in jet momentum. And this quantity Y is where it is kind of longitudinally in the experiment, so different phase space. And what you see is vast range in kinematic reach and in magnitude of cross section. And what's shown here is the ratio of one of these curves. I don't even know which one it is. Ratio of one of these curves to a very high order QCD calculation. And you can see, sorry for the scale, you can see the QCD calculation has some errors. That's the kind of the orange colored thing. It's about a 5% error. And here's the ratio of data to the calculation, and it's magnificent. Over many orders of magnitude in cross-section and in kinematic reach. So 5% agreement over a vast range. So precision, I've spent a lot of time explaining how complicated jets are. So the field has mastered it. This is absolutely magnificent precision, and jets are a precision tool to test QCD. This needed easily 30 years of development in theory and experiment and algorithms to connect the two. These algorithms are, by definition, IRC safe, infrared and collinear safe, and are continuously improvable. And this shows that jets indeed measure partons, measure quarks and gluons. So jets are a precision tool.
Didn't get the right-hand plot.
The right plot is the ratio to a perturbative calculation.
Which ones are the experimental points? What am I supposed to compare with what?
NLO Jet++ with CTEC 14 PDFs.
No. In the plot, So
Which-
there are these black dots.
Yeah, so
with
you're asking
some
which-
error bars,
You're
but
asking which one it is.
no,
this
no,
is-
no. I'm
Sorry.
asking which objects are supposed to be one. Is it I thought the black points with error bars are the experimental points,
This is
but
the
the
ratio of
experimental uncertainty is somewhere else. So
This is the ratio of experimental points to the calculation. So the calculation is by definition, the central value of the calculation is by definition at 1. It's just the calculation. There is an uncertainty on the calculation, and that's the width of that's the orange width. Okay, it's around 1. So calculation is by definition at 1. And now we plot the data with respect to the calculation. Okay. Is that clear?
And the band is jet energy scale systematics here.
I'm
So-
sorry, you are right, you are right.
Yeah.
I didn't look, but that is the experimental uncertainty.
Yeah.
Yeah.
So the way you should just look at it, that over a large PT range, the measurement is sort of matching with the theory. And the room of improvements are more on the experimental side because the experimental uncertainties have larger error bars.
Right, right.
Yeah. So
Sorry, I misrepresented, I misremembered. In fact, it's right here on the plot. The theory uncertainty is pretty small, and again, the quality is not great. Look at, just download my slides, it'll look better, or go to the paper, I have the citation here.
But what
Yes,
this
sir.
plot doesn't show, even in the theoretical uncertainty, the renormalization and factorization scale variation uncertainties are the most dominant sources.
It should be here,
Yeah.
that should be included.
This plot just doesn't reflect the phenomena that even in the theory uncertainty consists of the scale variation, then
Microphone.
yeah, there are components due to non-perturbative effects and PDF
Okay.
uncertainties, all these components. Among that, the largest component is the scale uncertainty. So the place to improve is still the perturbative QCD calculation.
So, right, so these scale uncertainties, we're probably getting a little, too detailed here, but these scale uncertainties, it sounds like you're more expert than this and that, always struck me as, I mean, you have to do something. So you take your choice of scale and you vary it up and down by factor 2. Why factor 2? Why not 3? Why not 1.5? You have to do something. It's a convention. Yeah, so they are, it's a definition. Seems to me what you're saying is one should always go to higher order, and that should thereby reduce the uncertainties. That's the way to reduce the uncertainties. Yeah. So, and this is from 7 TV, I think. That's right, this is 13 TV measurement.
13.
Yeah, yeah. All right.
Yeah, but this is with only 17 picobar inverse, probably.
There's a
later
relatively
we
old-
will
this is from
try to
20
improve the
From
limit.
2016, you've got
Yeah.
much more data now,
Yeah.
yes. So I think this makes my point well enough, I think. So these are all refinements, but this is surely good enough to make this claim without qualification. Okay? Okay, so that's so much for hadronic collisions. Now I want to go to nuclei. And, okay, so let's discuss jet production in nuclei. And there's one aspect that's very important to consider, and you've, I'm sure, seen it come by at this school, but I want to go over it again in my language and my perspective, so-called Glauber scaling of cross sections. Very important because this is an essential tool that we use to understand the fate of jets in the Quark-Gluon Plasma. So I'm going to spend some time on this Glauber scaling and the nature of hard processes in atomic nuclei. And we can think of, and actually, 3 scenarios in which this is relevant. One is proton nucleus collisions, another is electron nucleus collisions. This will be relevant at the electron ion collider. Hera did not collide anything except protons. And of course, hard processes in nucleus-nucleus collisions. And so what we need to understand is how cross sections scale just due to trivial geometry. And that's the baseline by which we can then judge how jet production, evolution are modified in a color medium. So we want to know if we just have these kind of so-called vacuum processes that we're studying in proton-proton collisions, how would their cross sections, how would their production rates be modified just by trivial nuclear geometry? Let's see if we can quantify that. So, okay, so here is the standard picture of Glauber scaling, so nuclear geometry and the scaling of hard process rates. So let's assume, let's make an assumption, and which we're going to test, okay? Let's make assumption that a proton colliding with a nucleus is an incoherent superposition of nucleon-nucleon collision, assumption. So we've got, some nuclear density, with Saxon, whatever you like, and we can define this normalized density by this line integral, normalized density rho, simple definition. And then we can integrate an impact parameter, we can integrate across the depth, and then get a nuclear thickness function that's a function only of impact parameter T. These are just trivial definitions, and you can have whatever model you like for how the nucleons are distributed in the nucleus. Okay, so now let's ask about cross-section. So we've got some inelastic nucleon cross-section. So the probability is a function for a given value of impact parameter to interact is this thickness function T times the inelastic cross-section. So probably not to interact is 1 minus. And so let's do that 8 times and take 1 minus that. So this is the probability for at least one inelastic collision of a proton. So we integrate over impact parameter. This is the probability for at least one inelastic collision of a proton in a nucleus. Yep.
Hello. So I'm not from the heavy ion community.
So I can understand.
I'm not from the heavy ion community, so I'm not much familiar with the thickness parameter, which is there in the formula.
Yes.
So is this something you purely fit and extract, or is there a theoretical way to sort of calculate it?
Right. So okay, the so-called Glauber theory and Glauber modeling, which we're going to test. I'm not just throwing this out there for belief. We're going to test it in a moment. So there's been generations of study of nuclear density distributions, right? I mean, people have been doing this really this is kind of low energy nuclear physics or electron, most importantly, electron scattering at, low energies. People do it at Jefferson Lab, people do it at, lower energy electron, form factors. So there's a lot of precision data of how nuclear matter is distributed. And so one relies on that. You can ask how much difference does it make? Now that's nuclear matter. That's not the distribution of nucleons. There are also correlations of nucleons in the nucleus. There are, you can't have nucleons on top of each other. They're fermions. You can't, you have to distribute them in some fashion. So certainly both positive and negative correlations of nucleons. It's not just, randomly distributed, but there's generations of data on nucleon distributions in the nucleus, and some people spend a lot of time trying to bring that together to come up with a very much data-driven distribution of nucleons in order as kind of the starting point for these kind of Glauber calculations. That answer your question? Yeah. So we're not just randomly. The simple thing is just a Wood-Saxon that's very convenient, and you can code it up in 20 minutes. But you can be more sophisticated. Also, neutrons and protons are not similar. There's a neutron skin. Very interesting, physics and the nature of neutron skins, especially in heavy nuclei. Does that make a difference if you're dealing with a measurement that's isospin dependent? Then it makes a difference. So you have to worry about all of these things. Okay. This is the nuclear mass A. Okay, so we're just, again, it's a simple incoherent superposition model. We've got A nucleons, and each of them, we assume each of them interacts independently. What's the probability for at least one nucleon-nucleon interaction giving a proton on a nucleus of mass A? So that's a essentially trivial formula. Okay. So now let's assume the process is hard. In other words, this cross-section is small, and we do a trivial perturbative expansion. You can do it in your head, and we get this pocket formula, very nice pocket formula. If this term is small, the probability of any one interaction is small, then the hard cross-section, the probability to produce a hard jet of a proton impinging on a nucleus scales as the nucleon-nucleon hard cross-section times nuclear mass A. Couldn't be simpler. Just straightforward. Okay. So that's conjecture. Does it work? let's see what data tell us. There are actually beautiful data which tell us whether this Glauber scaling works. And these are perhaps the most beautiful data, not so familiar in our field, but I like them. So I think it's worth spending some time. So what is this? This is from prehistoric times. Most people in this room weren't alive when these data were taken. This is an interesting hard process. This is muons on nuclei. This was at the CERN SPS, I think, fixed target. So this is a muon beam at 7 GeV scattering off nuclear targets with different atomic masses and just looking at the total cross section. What's the probability for a muon to interact with the nucleus? And you see the growth in cross section for deuterons, carbon, I guess that must be aluminum, copper, lead. And this line is A to the 1.00. In other words, scaling with precision with the mass of the target. And it works great. I don't know what photoabsorption is, that has been lost to history. But this data tell us that the muon nucleus cross-section scales with precision. I haven't done it in a statistical analysis, but it's pretty close to A to the power 1.00. Beautiful. Here's another more recent calculation from the NA50 experiment, also at the CERN SPS fixed target. And this is Drell-Yan production. We have a proton hitting a nucleus, producing a di-muon pair, so-called Drell-Yan process. And this is the scaling of the Drell-Yan production cross-section as a function of the mass of the nucleus. This is now normalized by the nuclear mass A, so rather than growing with A, it should just be at unity. We don't care what the absolute vertical scale is. We want to look at the A dependence. And this is the A scaling of the cross-section as we change the mass of the nucleus. And to my eye, perfectly flat. So no A dependence to Drell-Yan production as a function of nuclear mass. So Glauber scaling for these processes, these are leptonic initial state, leptonic final state, so no hadronic interactions, it's very clean, shows that this Glauber scaling and gives a very nice, well-defined hard interaction. This Glauber scaling works with precision. So now let's go to the LHC for photon production. So now we get super complicated lead-lead collisions, but photons don't carry color charge. Their production rate should likewise not be modified. You've heard about jet quench, should not be modified in the medium. This is now for the CMS collaboration. Let's look at photon production in lead-lead collisions. Electroweak bosons do not interact with the Quark-Gluon Plasma. I'm jumping ahead here, but no secret, you've all heard about jet quenching. We should see perturbative production rates in lead-lead collisions. So here's now the measured cross sections by CMS. I don't think I have a reference there. And here is now, so this is a quantity we'll come back to, so-called RAA, which actually measures the rate of production in nucleus-nucleus collisions relative to proton-proton collisions times the geometric factor. And if there were no nuclear effects in AA collisions, then RAA is normalized in such a way that it should be unity. And here is now these data in lead-lead collisions compared to proton-proton collisions calculated using this ratio, and no nuclear modification corresponds to unity. And these photon data, albeit with sizable error bars, their central values really center on 1. There's no evidence for nuclear modification to photon production rates. Also shown here are W and Z measurements, likewise, same argument. So Glauber scaling works for photons at the LHC, and even for Z production, same kind of business. So this is the experimental evidence that for sufficiently hard processes, this formula applies directly. Okay, yes.
Probably. This T time in the previous slide where you showed the thickness formula, etc.
Sorry, this one. Yeah.
It seems like T times sigma has a dimension. So how can
Has a which?
In the formula of inelastic total cross section, the T times sigma, it has a dimension.
No, it doesn't. No. Look at the definition. So rho is a dimension, is a density. It's GV per Fermi cubed times times one dimension. So T has the dimensions GV per
Oh,
Fermi
I-
squared. Cross section has the dimensions Fermi squared. So this is dimensionless. T is okay. Yeah. No. Yeah. This is, sorry, I skipped over that. This is right. So just check here. T, the dimensions work out. So it's dimensionless. Okay. Yeah. Okay. Other questions? Right. Good. Okay. So that actually concludes my lecture one. Just very briefly, so jets measure partons. We've found that that the technology has developed such that perturbative QCD and measurements really took decades, but this is this is already 10 years old. There's even better measurements now going to higher kinematics and very much greater precision. Jets are really a precision tool, and we understand jet production in the nucleus. So that, I think, is the end of my lecture one. I think I still have a little time. We can go on to lecture two. Yeah, so let's have any questions before I go on to the beginning of lecture two. Everything clear? Yeah, question in the back is Mike. Can you go to lecture two?
Sorry. The point is, when you are measuring jets in the experiment, so you have some algorithm, right? That I am.
Hard to hear you.
You have some algorithm, right? That
Yeah.
where you are choosing that this is my cone size, or these are the particle I am taking into account, like some momentum cutoffs are there and all. But when you are comparing this with the theory result, for example, there is this ratio to NLO jet plus CT
Yeah.
something. So how they are calculating, I mean, jets theoretically, because there how we can put a bound, some kind of bound that these are the particle I'm considering. Because yeah, I mean, in the previous week, Zoran was giving a lecture on this collisional broadenings of, I mean, and then so what he used to say that we are taking a parton, a high energy parton, moving into the medium, and it is being modified because there are many radiations and medium effects and all those things. So
Let's leave parton modification aside. Let's just talk about vacuum for the moment. Yes.
okay, so if there is no medium even, then in case of vacuum, if we consider let's say high energy parton, I mean just vacuum, so it will radiate and then it will lose some energy or something. But how can I mean draw these kind of cones? Because here you have a geometry, I mean from where you are doing experiments. But then how these theory people are doing this? Because I'm not in this field.
May I rephrase it? I think what you're asking is, so I went a lot of talking and hand waving about this algorithm, that algorithm, midpoint cone, anti-KT, and so on. And then I said, we want precision comparison between data and theory. And I spent a lot of time talking about how complicated it is to get the answer out of the data. Are you asking, well, how do we put all that together? Is that your question? Basically. So the answer is these algorithms, anti-KT or midpoint cone, for the moment, these are just names, words. They are also applicable to the perturbative or not. And my understanding, and I'm sure there are people in the room who know much more than I do, these algorithms, anti-KT, is equivalently applicable to the perturbative calculation. You can use the perturbative calculation and apply the anti-KT algorithm to it and get the prediction for the anti-KT jet production cross-section, which is different. And we have direct experience with this also when we're measuring jets in star. There's another one called midpoint cone, which is a tevatron, a lot older. And there's a lot of discussion some years ago. The calculations, if you take the same perturbative calculation and you apply anti-KT and you apply midpoint cone, you get different answers because they are reconstructing different objects. In some cases, they include the radiation in this algorithm and not in this one. So jet is a definition at both the experiment and the theory level. You saw how complicated they are. There's no way around that. The only solution, and this, I hope I've convinced you, is what the field has accomplished, is that we have a definition that can be applied with precision to experiment and theory in the same way. So we have multiple different definitions, but internally within each, as long as we're careful, we can do meaningful comparison of experiment and theory. So did I get your question? Did I answer your question? Okay. More questions before we go on? Yes.
Why do we only compare with the proton and the nucleus calculations? Why not just neutron and the nucleus collisions?
So I missed that. Why not?
Only protons and the
Proton nucleus.
nucleus. Why not a neutron and a nucleus?
Neutron. If you give me a neutron beam, I'd have to be happy to do that. They're harder to produce. So the accelerators, they produce charged particle beams. That's the nature of physics. I mean, people study neutrons, but they're very hard to control. So no chance of producing of accelerating neutrons. Okay, it's just the nature of it. But people can produce pion beams. You have secondary beams, for instance, CERN SPS. There are muon beams. There are high energy neutrino beams. I mean, there are all kinds of different projectiles, just not the high energy. Well, I guess you could do a kind of a spallation and probably get some neutron beams that are very, very hard to control. But LHC produces enough protons, and that's good enough. Okay. More questions before I go on? Got one more at the end here.
I was asking about the plot in the Drellian process. You get independent of A thing. So I didn't get the point why you get that independent of A.
What? So, right, so if you remember the formulas, the slides are already gone. So the conjecture, the guess is that the hard cross-section scales as a nuclear mass. That's the conjecture. Now we want to test it. So we did an experiment. We have a beam. It was a muon beam colliding with nuclei of different size. And we're measuring, and that, so I didn't talk about muons, but this is also a very beautiful, it's really a scalpel, hitting the nucleus. It's also a hard process. So we want to know the cross-sectional probability of a muon interacting with the nucleus as a function of the nuclear size. The prediction from these simple Glauber assumptions is that that cross-section scales precisely as the nuclear mass A. So somebody did the measurements from carbon up to lead and measured the cross-sections and found it goes as A to the 1.00. And then this Drellian, which was basically the same thing, but the cross-section was divided by A. Also Drellian, you got a proton coming in producing a dimuon pair, which doesn't interact. And that cross-section also, within the precision of the measurement, scales as A. So it's testing, that is the test of the Glauber assumption. So when we come to nuclear collisions and I use Glauber scaling, that should give you some confidence that there's something behind it. It's not just a guess. Okay, okay. Yeah, one more.
The scaling that you showed, muon nucleus collision. How low in muon beam energy can one
That was just
move?
7 GeV.
No,
just
but
one fixed. The idea was just fixed energy and just change the mass.
If one goes down to 1 GeV, will one still expect?
Good question. No idea. More questions?
Yes.
Yeah, one more. You have a question up there? Or?
So in this,
Oh, I'm sorry. Yeah.
In the picture where you showed this TA for PA collision.
Yes.
So do you consider any dimension of the proton, or proton is it just like a point particle?
Of the project in the nucleus, in the Glauber modeling of the nucleus, the protons have a width. The nucleons have a width. They can't overlap. That's how you. I mean, there's a question before about how you model the nuclear matter. So you have to keep account of the fact that nucleons have some repulsion. The incoming proton size, I don't think people account for that. It's just a cross section. I mean, it's just that the physical size doesn't matter. We're talking about cross section.
Sorry,
So there's an
proton?
input nucleon cross-section, which is measured. We use the proton-proton cross-section at the relevant energy. So that has some 70 millibarns or something at the LHC.
Okay. And in this calculation, the distribution of this all the nucleon in the nucleus is in Monte Carlo distributed randomly. That means
This is what I was saying before, is that the simple thing to do is random, but nuclear complicated. We know there are correlations between nucleons within the nucleus. Does it make a difference? I mean, insofar as we're dealing with small cross sections, it may not make a difference. And people have tried, using the world's data on nuclear matter. There are vast, sets of data over generations that nuclear physicists have, they've measured form factors, they've measured correlations. All of this has been taken into account in various variants of this Glauber modeling. And the effects are relatively minor, but you can do it. There's no formal barrier to doing it. The question is it really necessary to get the precisions we need? And I would say overall, kind of trying to build in, higher order nucleon correlations. Yes, the physics is there, but I don't think it really matters for this kind of stuff. We eventually put a systematic error bar, and the uncertainties from other physical sources are greater than any such effects. So I think I mean, maybe there are other comments here, but I think a relatively simple model of nucleon distributions within nuclei is generally kind of good enough, because refining it would be overwhelmed by other uncertainties.
Thank you.
Okay, one last question here.
Okay. So question on this photon rate calculation. So you compared with the lead-lead collision data with the proton-proton collision. So you see one, right? The scaling.
Right. So I showed photon and Z production in lead-lead collision.
Yeah. So these photons also include the the decay photons, or
I have a hard time hearing.
means the photons include the decay photons only, or what photons are they?
These would be direct photons.
It should be direct.
This is only hard photons, very hard photons. Sorry, the plot disappeared, but these are very hard photons.
Okay.
So really, really hard processes.
High PT photons are direct photons.
Okay. So now we're going to move to the main topic, namely jets in the Quark-Gluon Plasma. And okay, I put a little recap, not knowing that, okay, we don't need to do that. I'm going to start a little differently than the other speakers and talk about the nature of many-body physics. And this is a very beautiful paper from 1972 by a very great physicist from a different field. Philip Anderson won a Nobel Prize for his work in condensed matter physics. And this is a famous paper that everybody should read. It's really foundational to a branch of science which is really pervasive and has direct relevance to what we're doing. So the title of it is Published in Science. I have a copy of my laptop. I can actually make it available, probably not violating any copyright. The title is More is Different: Broken Symmetry and the Nature of Hierarchical Structure in Science. And so what I've done is pulled out, some of the text, and well, let's go through it a little bit. Just look at the underlined parts here. Nothing to do with the Quark-Gluon plasma, everything to do with the nature of many-body physics. So Anderson writes, the reductionist hypothesis may still be a topic for controversy among philosophers, but among the great majority of active scientists, I think it is accepted. All animate and inanimate matter is controlled by the same set of fundamental laws. If everything obeys the same fundamental laws, then the only scientists who are studying anything really fundamental are those who are working on those laws. That's a kind of a statement of the conventional wisdom as of 1972, but maybe not. Solid state physics, plasma physics, perhaps also biology are extensive, not intensive. High energy and a good part of nuclear physics are intensive, looking intensely at the finest scales. Once new fundamental laws are discovered, a large and ever-increasing activity begins in order to apply the discoveries to hitherto unexplained phenomena. Thus, there are two dimensions to basic research. The frontier of science extends all along a line from the newest and most intensive research to the broad and well-developed web of extensive research activities based on research of the past decades. So this again is a kind of a reductionist idea that the fundamental research is about the most microscopic mechanisms, and eventually with the passage of time, you can apply those more broadly. But here's the kicker. And now he writes, I'm just pulling out a few phrases here. You really need to read the whole paper, it's very beautiful. Now he writes, and this is really his manifesto, the behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a simple extrapolation of the properties of the few particles. Instead, at each level of complexity, entirely new properties appear, and the understanding of the new behaviors requires research, which I think is as fundamental in its nature as any other. So this is the manifesto of emergent physics. There's fundamental physics to be understood at every scale. This reductionist philosophy that you start from the most elementary interactions and you can derive all of biology from Maxwell's laws really doesn't work. So I think that's a very beautiful starting point for our discussion about the Quark-Gluon Plasma. Let's now consider matter. When you pack, and this is now deriving from Morrison's statement of his manifesto, when you pack many particles tightly together, new things happen. And the term of art, and this also dates back to Morrison, is emergent. You get emergent phenomena. These are all around us. The phase diagram of water. We may not know all the details, but we're certainly familiar in everyday life and how water behaves in its various phases. Ice, and the melting point of ice, and the fact that we can skate and ski, boiling on the stove, all of that is familiar to us in our everyday lives. So the phase diagram of water is quite complex and is likewise emergent. You can't derive this from Maxwell's equation. There's likewise a phase diagram of QCD, and you've seen this before in this series, in this workshop, I'm sure. Unfortunately, in these two diagrams, heating and compressing are inverted, but we can deal with that. And so you've seen all these features here. So this one has been explored in detail by chemists and physicists over many generations. This one, well, we're now a couple of generations in, but I would say we're still really in the beginning or middle phases of exploring the QCD phase diagram. This is a cartoon, this is data, this is a cartoon. We are really only starting now to be able to quantify this phase diagram. People are using the lattice to study it. People are doing beam energy scans at RIC to study it. I'm sure you heard about that. And likewise, we are using high energy jets to study aspects of this phase diagram. And so now the focus at colliders, well, Rick had this beautiful beam energy scan, but my focus and the focus of high energy jet studies is really along this kind of this baryon-free axis. This is a baryon chemical potential. One walks along this direction as the baryon imbalance gets larger. We're going to focus here on the baryon-free region, which is the central production region at the RIC and LHC colliders. So we're going to work along this axis. And people have studied the phase diagram on the lattice. And I like this lattice diagram. This is a lattice calculation at a 0 net baryon number here along the axis. It's a relatively old calculation, and maybe some of the lattice experts can provide me with a newer one, but it has some features I like a lot, which is why I continue to use it. And so what we show here is a lattice calculation, the 0 net baryon number, of the energy density over the 4th power of the temperature. And that's a nice thermodynamic quantity because it's actually proportional. So it's actually proportional. It counts the number of degrees of freedom in this QCD matter, or this energy density of 4th power is of the temperature, just counts degrees of freedom. Let's just say that. And so this is now familiar, should be familiar to everybody. At low temperature, the number of degrees of freedom is small, hadronic matter. There's some kind of transition. It's not along this axis. It's not a finite order transition. It's a crossover, similar to the ionization of an atomic plasma. So it occurs over some range in temperature. And again, this is not the latest calculation, but that's not my main point here. And these various variants of the calculation are not important either. So just the general features of what I'm interested in down here: hadronic matter, up here, deconfined matter. So there's some kind of crossover. And now comes the feature of this plot that I really like a lot. And that's here asymptotically. So what is SB? This is the Stefan-Boltzmann limit of non-interacting quarks and gluons. So you would expect naively, or you would expect, asymptotically, not naively, asymptotically, extremely high temperatures where the coupling is arbitrarily small. Quarks and gluons should just interact freely. You should get a simple Stefan-Boltzmann gas whose degrees of freedom are just counting up the number of degrees of freedom of spin and flavor of the quarks and gluons in the plasma, however many quanta nature gives us. That's the Stefan-Boltzmann limit here. What does the lattice calculation tell us? Even at 1,000 MeV, and you can get your eye, it's not going to reach the Stefan-Boltzmann limit anytime soon. There's a gap, about a 15% deficit in the number of degrees of freedom in the lattice calculation relative to the asymptotically free Stefan-Boltzmann limit. That is super interesting. There's a very slow convergence to non-interacting Stefan-Boltzmann limit, but the degrees of freedom in the lattice plasma are not non-interacting. They're interacting in some form. There's some kind of complex bound states of quarks and gluons. Maybe this is the origin of the strongly coupled plasma. I actually think this deficit is what's driving all of Quark-Gluon plasma physics. It's this deficit and the nature of these bound states and how they drive all of the dynamics we're seeing in hydrodynamics and jet quenching and all of that. It's this deficit we need to understand. And as I'll get to at the very end of this lecture, which is got a lot of slides, can we understand the quasi-particle nature of the plasma? Are there experiments we can do to really uncover the complex bound states that are within this plasma? I have a separate question to lattice people. It's a general question. I don't know the answer. Are there things you can do in a lattice calculation to reveal the nature of the bound states that are generating this deficit? So that's, it was important for me to make that point. This is kind of my essential introduction. So this is a lattice calculation about equilibrated quark-gluon matter at very high temperature. But I think there's a direct connection to the jet physics we're going to talk about. Can we explore this deficit by scattering experiments and see something about the nature of the plasma here? And is this indeed what drives all of the complex, beautiful phenomena we're seeing in terms of perfect fluids and jet quenching? And well, you know very well that these experiments are carried out at these different colliders. I've already shown that. And let me stop there, and I'll start next time with really discussion of jet quenching. Okay, thank you. So maybe questions, maybe we should ask any questions about this before we break. Yeah.
A comment. So you said, so there is a recent calculation on lattice which goes up to 170 GeV, and you see this gap is still there.
It goes up to
170 GeV.
You mean way to the right?
Yeah.
And the gap persists.
There, yeah.
What's your understanding of the gap?
So it is kind of well-known thing. It's magnetic scale in the QCD.
Okay.
It's non-perturbative even at infinite temperature. So that is what plays the role.
Comment here. I look forward to your comment. I was hoping for a comment.
Not that I understand very well what's going on there at high temperature, but if you look at this curve, you see it's pretty boring, it's flat, okay? Running of the coupling constant is logarithmic. So
It's
think
running on top
the
of it.
running of the coupling constant is logarithmic.
Yes, yes.
It's very, very slowly.
Yes.
Now, the statement about degrees of freedom and the formula you have written, T to the 4 times G, is valid for massless degrees of freedom. Okay? Now, one of the first things that happens in an interacting system is that quasi-particle acquire mass.
Yes.
Okay? And now, if there is a mass,
All bets are off.
yes, there is no real issue. The mass of the quasi-particle.
So I would be happy with a statement that, we are not, somehow gluons are acquiring mass. Also interesting.
Yes.
Also interesting.
And it's worth,
I'm not sure- I'm not-
exploring experimentally what these quasi-particles
Yes,
are. I don't
I'm
know.
not sure it's fundamentally different. I mean, a particle that acquires a mass, this is not an asymptotically free point particle. So maybe my term is a little loose here, complex bound states, but a particle that acquires a mass, something's going on. Okay, yeah.
Quarks acquire mass.
Yeah. Yes. Good.
But I guess the physics is the point I'm trying to make. This is not
Microphone.
Yeah, this is not really the strongly coupled Quark-Gluon plasma that many people advocate. I mean, that's my own view, but
There's a question mark at the end of my statement. Good. Okay. Any questions, or we doing a proper break now? Okay, I think we're done. Thank you.